You don't have to think too long to figure out a good idea for implementing this data structure. And the key is the thing we were just discussing. It's the fact that find gives a unique ID for each element. So to implement that, we could use an array where we hold the IDs. This is the idea of the quick find algorithm. Quick find is an eager algorithm. We're going to compute the identifiers for each of the elements as quickly as possible, as soon as we can. And so our ID array, if we have 3 connected components, will hold just 3 values. So here 0, 5, and 6 all have the same ID, which is 0. 1, 2, and 7 have the same ID, which is 1. And 3, 4, 8, and 9 have the same ID, which is 8. And so this array actually has all the information we need in order to answer or to implement the dynamic connectivity problem. We can implement both union and find simply using this array. As I mentioned before, the implementation of find is straightforward with this array. All we need to do to check whether 2 things are connected is to look up their ID. So the find method is just a simple array index. The union operation is more complex here. Suppose I have 2 elements like 1 and 6 that are not connected and I want to union them. Well, I've got a lot of things I need to change, so I need to pick a winner here. So either 1 or 0 is sort of a logical winner or champion for this contest. If we choose 1, then what we need to do is go through this array and find all of the occurrences of the loser, 0, and replace them with the champion, 1. And that's not hard to do. We're going to use a loop. It's important to note, though, that there's no structure on this array that tells us where the zeros might be. So pretty much we're just going to have to use an exhaustive algorithm to loop through the array. So here's a demo of this done by the authors of the text, and you can see as we union things in the diagram, they're also being unioned in the array. And in fact, the image here, or the drawing, is completely redundant with the array. So if you have the drawing, you can come up with the array, and vice versa. This animation we're walking through, you can see, is that we're unioning things together, choosing a champion, and going forward. Let's walk through this a little bit more slowly, actually looking at the code itself. I've written a test file that will allow you to try various union find combinations on different union find structures that we're going to consider. Let's just walk through the output of this and see what happens. And I think you can get a feel for how the quick find algorithm works. So here is the initial array, and I'm showing it here in Eclipse. It's printed out just the numbers 0, 1 through 3, 4, up to 9. And you can see that shown as the array, where each element of the array is simply its own number. Now, what we're first going to do here is join 4 and 3. And what that's going to do is reduce the number of connected components. So we're also showing this in the Eclipse output. The first number before the array is listed is the number of distinct components. So when I connect 4 and 3 here, I'm going to reduce the number of connected components by 1. Note that when 4 and 3 are joined, this is an asymmetric operation. Somebody's the winner, somebody's the loser. And in this case, 4 is the loser. What happened? 4 is no longer its own boss. You can see here in the array, 4 is now pointing to or referring to 3. And in the picture, you can see this as 4 is an arrow to 3. When we join 3 and 8, well, 3 is now going to be the loser, and 8 is the winner. So 8's going to be on top of 3 and 4. Now, note that when 4 and 3 moved over to 8, they both switched. So I didn't just change 3, I also changed 4. So they both move over to join the new champion, which is 8. And this is going to continue. So if we join 6 and 5, in this case, 5 is the champion, 9 and 4, we're picking 4. The choice of champion is arbitrary, but the way the authors of the textbook have coded the algorithm, the second element is always the champion. So here we'd say that 4 is the champion, but 4 is already a loser. So we've got to pick 8 instead. So what we're going to take is not 4, but the champion of 4. And we'll make that the new champion. And in this case, 9 is now a loser. And so we've got 3, 4, and 9 all under 8. 8 is becoming very powerful. Then we'll join 2 and 1 here. And note that 1 is the winner. If we then try to join 8 and 9, nothing happens because they're already connected. If we join 5 and 0, what's going to happen? Well, in this case, 0 will be the champion, and therefore we'll have 0 above 5 and 6. Then joining 7 and 2, 2 is a loser. So 1's going to be the champion, and we'll get 1 over 2 and 7. And finally, 6 and 1, well, 1 is winning very nicely here, and it's going to get some more subjects. So 1 has now got 5 subjects. And that's the end of this example. This is the example from the textbook. It's interesting to look through some different examples, though. What happens? What's the best thing that can happen? What's the worst thing that can happen? Let's try joining things in this order. We'll try joining everything to 0 and just sort of see what happens. When you can see what's happening here is because the second element is always the champion, what's happening is I'm updating everybody to point to that new champion. What happens instead if I always pick 0 to be the champion? Well, in that case, everybody's just going to go under 0. What happens if I choose 1 to go under 0, then 2 to go under 1, etc.? Well, in that case, it's going to be the same thing. Everyone's just going under 0 because the champion of 2 is 0. And that's the one I'm choosing on the right-hand side. So you can see 0 is going to get floated along. It kind of looks like a crowd where you're passing somebody overhead. It's like concert action. Okay, and let's see. Let's just reverse that around and see what happens. Well, if I join 0 to 1, well, now 1 is the champion. I'm going to join 1 to 2. Oh, well, this is just that thing where the numbers floating across, different number across the top. What happens if I reverse the order of those two? Well, the second element is going to be the winner every time, and so the number is going to change as it did up above. Let's try some other examples. Here's 16 numbers, just trying to join them together. First, we'll pair them all up. Then we'll sort of put them, the groups of 2 together. Oh, there's a group of 4 now. We'll group another 4, another 4, another 4. Then we'll group those groups of 4 into groups of 8. Then we'll group those groups of 8 into one big group of 16. Okay, so that's interesting just to see the pattern, how it works. And I always like to do something random. So here's some random data. It's a random test. I don't know what it does. Let's find out. There's 12 nodes here, and it's just sort of randomly putting them together, and that's what happens. All right. Of course, we're interested in performance as well. What's the performance of this algorithm? Well, as you can imagine, the connected question is very fast to answer because it's just 1 or 2 array lookups. And that's great. That's a constant time algorithm. So in fact, you can see that reflected here in the output. If I do in operations, where in is increasing, so here I'm going up to 262 connected questions. Well, it's more or less just double what I had before. The numbers are really small, so it's very noisy. But essentially, for doing twice as many is connected problems, I'm getting twice the amount of work. So each one of those single connected questions is constant time. Instead, what's happening with the union operation? Well, not great. So as I double the number of union operations I do, I'm not doubling the amount of time, I'm quadrupling it. And this is all sad and bad. So I've got a quadratic algorithm. And you can see here for just 260,000 elements, I'm already taking 51 seconds to union them together. So that's the quick find algorithm. Let's think about how we'd code it up. We need an array of IDs. We need a counter to keep track of how many connected components there are. And what we're going to do is initialize the array so that every element has a unique ID. And that's straightforward because we have in elements. We can just pick the numbers 0 to n-1 as the IDs. Computing the count, the connected predicate, or find, all of these are trivial. We can do them immediately just using the variables that we have, the count and the ID. The only interesting operation here is the union operation. And what we'll do here is pick the ID of the loser, pick the ID of the champion, then go through the array, and anywhere we smell the loser, we'll replace him with the champion. That's going to update our array. Then we just need to update the count to say we've reduced the number of elements. Note that I'm only going to do this loop if the elements aren't already connected. This is obviously a linear time algorithm. Why is that obvious? Well, because I am going through every element of the ID array, and there may be an arbitrary number of them. So we'll go through every one. Linear time algorithm. So that's the quick find algorithm. It's great because it's really easy to understand, and it's correct. It solves the problem. The only difficulty here is that the union operation is a bit too slow. So this is called quick find for a reason. Find is constant time. It is blazing fast. But that union operation, it's a loop through the entire data structure. And you can see as our data structure gets large, well, it's getting really slow. For just 260,000 elements, this was almost taking a minute to add those elements or to connect those elements in the array. So for 260,000 elements, it's taking work proportional to 260,000 squared to do those 260,000 operations. And that's just not going to scale if you want to deal with large data. So what do we do? Well, one temptation might be to just buy a better computer, but that's not going to help you out because as computers get bigger, their memories get bigger, the problems we want to solve get bigger, and getting a bigger computer, if you want to solve a problem 10 times as big on a computer that's 10 times as fast, well, you might think that would be fine. But if your algorithm's quadratic, it's still going to be 10 times slower because the problem size is bigger. So we're always going to have a difficulty with these kind of algorithms with quadratic performance. So what can we do? Well, the problem here is this damn union operation. If we can make union faster, then maybe we can make some progress. So let's think about that.